Morning, everyone. So I hope you people are doing good. Okay. So today, now, let me check all those things. So I hope my voice and video is clear for you. Good morning. Cyclone generating and it will pass from coastal region of Gujarat and Mumbai tomorrow at 100 to 100 kilometers per hour. Be safe. So the people who stay in Gujarat and Mumbai, please stay safe. Okay, fine. So now let's start. Yes. Okay. So yesterday we have been discussed. Let's see. See, these points are very important actually. Yesterday we discussed about the different definitions. The most important definitions. Yes. So in a case of the shallow foundation, what are the important definitions that we have been discussed yesterday? Now let's see. Look, we discussed about some of the definitions like whatever the total pressure acting at the base of the footing as gross pressure, means irrespective of the load, whether it is a column load or backfill or self-weight of footing, everything, if you consider whatever the total pressure at the base is nothing but the gross pressure. Now, if you remove this backfill, whatever the backfill self-weight is going to be gamma d, then that is going to be net pressure. So the total pressure acting at the base and what is the net pressure acting at the base. So these are the things that we have been discussed, and based upon this, I told you again what is meant by ultimate bearing capacity. So whatever the total pressure you apply, out of that the soil will take maximum without any shear failure is known as ultimate bearing capacity. Okay, but you know that in the ultimate bearing capacity, this soil is going to be resist all the, see, this is nothing but the ultimate bearing capacity. And in this ultimate bearing capacity, some portion of the soil has been resisted the self-weight from long time. So now we need to worry about whom? The external load. So if you remove the self-weight from the ultimate bearing capacity, then you can get the net ultimate. So that is the maximum net pressure that I can take. But when you are design, you have to design for safety. So that safety is nothing but net safe. So the net safe is going to be net ultimate by factor of safety, and then you are going to add self-weight known as a safe bearing capacity, and without any excess settlement QNP. And you know that the design consists the general requirements for the foundation is a no shear failure and no excessive settlement. So which means without any shear and without any excessive settlement, that pressure is going to be net allowable pressure, the net pressure that soil can take safely without any shear failure and excessive settlement. And now the design condition is going to be always the net pressure that you applied on the soil mass, whatever the net pressure that we applied on the soil mass. What is meant by net pressure? If you remove the self weight from the gross pressure, that is going to be net pressure. then that net pressure should be always less than or equals to net allowable bearing capacity. And you know that QNA is going to be smaller of QNS and QNP. So generally I said most of the soils fails by shear failure. So now whatever the net pressure should be less than or equals to net safe bearing capacity, because most of the soils fails by shear, and this is the final condition I have given you. I'm telling you, you need to be good with the terminologies. Ultimate, net safe. Now, my dear students, if you want to design, you need to look over the QS. Yes or no? What is the representation of this one? What is the representation of this one? Whatever the gross pressure means, whatever the pressure you applied should be less than safe bearing capacity of the soil. I am a soil. No matter whatever the load you apply, I don't care. If you want to apply self weight, external load, whatever it is, the total pressure acting on me should not exceed the safe bearing capacity of the soil mass. Safe bearing capacity of the soil mass. So now in order to find out the safe bearing capacity, QS, how can you find out the QS? QS is nothing but QNS plus gamma D. How come you find out QNS? QNU by factor of safety. And how come you find out QNU? Net ultimate. QU ultimate minus self weight. So if I can find out the QU, from there I can find out QNU, from there I can find out QNS, then I can find out the QS. Okay. Now, so that's about a brief review about whatever the discussion we made yesterday. So now let's come to the remaining things. Yeah. So this was the portion up to yesterday's. Now let's see the remaining thing. Now, compensated raft foundation. Compensated raft foundation. So what is meant by compensation? What is meant by compensation? If you lost something and you are going to be compensated with some other thing which is equivalent to the loss. So you lost something and you got compensated with some other thing. Yes. So here, what is the meaning of a compensated raft foundation, sir? You know that when does the raft foundation is going to be used? Yes or no? Whenever the total area of the isolated footings are covering more than 50% of the construction area, or wherever you want to reduce the uneven settlements, then you are going to go for the raft foundation. So now what is mean by compensated raft foundation? This is a very beautiful topic, and now I'm going to resembles. I'll ask you before going to this one. I hope you might have been whatever the public buildings you have been gone through, whether it be shopping malls or whether it be cinema malls, means cinema halls, or whether it be any multi-story building which is having a basement floor, So especially right now, everywhere in every city there are big malls, and you know that most of the guys goes to the malls to see the malls only, and even I know that. So my dear students, those who goes to malls, it's not only the malls, but if you observe the basement floors, so for every shopping mall there is a basement floor. See, we don't construct the basement floors for the residential buildings or for the apartments, but we do construct the basement floors for the commercial buildings. And you know that the basement floor is going to be located below the ground level or not? Means whatever the parking we say now, that is nothing but the basement floor or cellar, I can say cellar. So that basement floor or cellar lies above the ground level or below the ground level? It lies below the ground level. Sir, why for every commercial building or public building there is a basement floor? See, we think that the cellar is for the parking purpose. We do feel like that. But my dear student, it's not about the parking purpose. Now you are going to see what is the advantage of that cellar. So now let's see. Let's come to the same thing. So let's take this as a ground level, and at certain depth D, before the construction, what is the self weight? You see, please tell me. Before the construction, what is the self weight? Gamma into D. That's, you know that. Now, I want to construct a structure. And when I want to construct a structure, I need to do the excavation or not? Now let's go for the excavation. Now, I have done the excavation over here. Yes. Look, in the same So in the same depth D, now what is the pressure you are going to see earlier? The pressure that we have seen in the earlier is gamma into D. So that's nothing but the self weight. And don't ask me how it came, sir, gamma D. So that's nothing but the self weight. Now I am saying your raft. What is mean by raft? You know that raft means, you see this? Yeah. Raft means for the entire foundation, you are going to provide a single mat, right? This is a single foundation on which all the columns are going to be rest. Yes. So now let's take the entire excavation bed. You are going to fill with the steel, and then you are going to pour the concrete. See, through this, the pillars are going to become up. Means columns are going to be comes up. So now let's construct a footing. So now let's see. This is the plane along which we require the stress, and this is the base of the excavation. Okay, fine. This is the base of the excavation. So now you see, we are going to construct a raft. Yes. So whatever, this is nothing but the raft foundation. And on this raft, we are going to construct the columns. See, this is nothing but the floor, right? Basement floor. And if you observe over here, we are going to construct the wall also here. Yes, we do construct the wall. See, for the basement floor, you can see the slab, raft, and you can see the side walls also. Yes, I'm not representing the side wall. Now, you tell me, whatever, this is nothing but the ground level, and this is also ground level. So the basement floor is lying below the ground level or above the ground level? Below the ground level. And this is nothing but the raft. So now, through which you are going to raise the columns. Yes. So through which we are going to raise the columns out. See, don't think this is a combined foundation, that is going to be a raft foundation. Now, my dear students, just imagine and tell me, basement floors are going to be lies below the ground level. Yes or no? Yes. And are you going to fill the soil mass in the basement floor? Are you going to fill the soil mass in the basement floor? No, right? And again, you are going to construct the slab right here. Again, you are going to construct the slab. So we do construct one more slab over here. So now, whatever, this is nothing but the basement floor. And in this basement floor, if you observe, this is known as basement floor. And is it going to be with backfilling or without backfilling? You tell me, please. This is a basement floor. You have been in a mall. So let's take it as a B1 or B2 or UB1 or whatever it is. Are you going to fill the soil mass over here? So this is the place where you are going to keep your bikes or cars parking. You can see at the bed there is a concrete bed and sides there are the pillars. Can you observe over there? Yes or no? Yes. And this basement floor is going to be without backfilling or with backfilling? Without backfilling. This is without backfill. So then what is the meaning of the compensated raft foundation, sir? Now, the meaning of the compensated raft foundation is, if this is going to be Q1 and if this is going to be Q2 and whatever the area. So now, whatever the gross pressure acting over here is nothing but total load by area of footing. Look, my dear students, if you keep your palm at the base, what is the total pressure that you can feel? Tell me. The total pressure that you can feel is only the load coming from the structure by the area of footing. See, in this case, I have done the backfilling. I have done the backfilling. When I do the backfilling, apart from Q by area of footing, I can feel the self weight of the soil also. Just simply keep your palm. You can feel the load from the structure and you can feel the self weight. But if you look over here, is there any backfill? No. When there is no backfill, this is nothing but a without backfill. Now, what is the meaning of compensated raft foundation, sir? The meaning of compensated raft foundation is, in compensated raft foundation, the gross pressure acting after construction is same as self weight of soil before construction. What is the meaning of this? whatever the self weight of the soil mass over here, that's nothing but gamma d. And before the construction, what is this gamma d? Self weight. And if I want to construct, I need to excavate the soil, then I'm going to construct the structure. Yes or no? So my dear students, let's say before the construction, the self weight of soil is 100 kilopascals. Let's say the self weight of soil is going to be 100 kilopascals. Now you want to construct a structure. Now you excavate the soil mass and you excavate the soil and you construct the structure whose total pressure is exactly equals to 100 kilopascals. So before the construction, 100 due to self weight. After the construction, 100 due to gross pressure. Then what is the net pressure? What is the net pressure? I told you the meaning of the net pressure. Net pressure means pressure at the base of footing by excluding the self weight of the soil. Okay. So in the case of the compensated raft foundation, just now I said, so whatever Q is nothing but gamma D. And you know that net pressure is nothing but gross pressure minus self weight, then it is going to be 0, which means in the case of compensated raft foundation, the net pressure acting on the soil mass is going to be 0. Array, when the net pressure is going to be 0, I told you what is the design condition, please. The net pressure is going to be less than or equals to net allowable bearing capacity or not. When the net pressure is 0, then there is no settlement, then there is no shearing. Yes or no? In simple words, net means extra pressure. In simple words, net means extra pressure. If the extra pressure is going to be 0, do you think the soil is going to be undergo any settlement or any shearing? No. That is the biggest advantage of the basement flows. Sir, if I do the backfilling, what happens? Tell me. If I do the backfilling, then Q is nothing but Q by area of footing plus gamma D. Yes or no? See, this is with backfill. So if I add backfill, then what is the gross pressure? Q by area of footing plus self weight. And before self weight. So now if you add the backfill, never the gross pressure is going to be same as a self weight. So if you add a backfill, then there is a net pressure. Keep that in your mind, my dear student. You have to reduce the net pressure as much as possible. So always you need to keep the net pressure less than or equals to net allowable bearing capacity. So if net pressure is going to be 0, that's going to be safe for us. And because of this reason, why most of the buildings nowadays are opt for the basement floors. Yes, simply, what is the mean by basement floor? Earlier there is a soil mass. Yes, this is the soil mass. Now simply I remove the soil, and in place of the soil, I am constructing the structure. I remove the soil and in place of the soil, I am compensating with the structure with the same pressure. Earlier soil was 100. Now I remove the soil and I compensated with a structure whose pressure is going to be same as 100, so that the net pressure I am adding on the soil is 0. So basement floor are example known as a cellar or basement floor. That's one big advantage of the compensated raft foundation. Now, so my dear students, now if anyone asks you, what is the foundation? What is the foundation for a structure having a basement floor? What is the foundation for a structure having basement floor? That is nothing but the raft foundation. So if you want to construct the basement floor, you must have to provide the raft foundation only. You cannot do it with the isolated or spread foundations. So, my dear students, sir, one of the students, sir, then for compensated rafter foundation, total load from multi-story building is equals to load of the soil excavated. But how is it possible? Because load from multi-story building is very high. Yes, my dear student, it is very high. But if you are going to be apply exactly equals to the self weight, then the net pressure is going to be zero. Now I'll tell you one more example. Sir, if the load from the multi-story building is going to be very high, now just imagine, okay, you want to construct some 20-floor building, and you know load coming from the structure is going to be very high. And if you backfill the soil mass in this space, then obviously the gross pressure is going to be much more higher or not? Yes or no? And instead of that, I remove some portion of the soil mass, and whatever the portion of the soil mass I remove, that will be compensated by the structure. That will be compensated by the structure, so that the resultant net pressure would be less or not? See, either we make to the net pressure zero or we make net pressure less. If you are going to be apply the pressure exactly same as the self weight, exactly same as the self weight, then that is going to be compensated raft foundation. So can we use this raft foundation in seismic zone? In seismic zone, it does not depends upon the foundation. It depends upon the whole stability of the structure. Yes, after foundation depth depends upon the weight of structure. The foundation, the type of foundation depends upon the weight of structure and at what depth. The soil also. Yes, there is a retaining wall also. See, this is nothing but the retaining wall. This is a retaining wall. Okay, there is a retaining wall is there. My dear, one of the student is asking us, please draw the retaining wall. So I am drawing the retaining wall also here. Whatever, this is nothing but a retaining wall. So that's it about these conditions. And remaining things will be discussed in the doubt clearing session. Today there is a doubt clearing session. So now that's about the compensated rafter foundation. Now let's go for the next. Modes of shear failure. Modes of shear failure. So there are different modes of the shear failure. There are different modes of a shear failure. Keep that in your mind. 1 minute. Yeah. So the different modes of shear failure are, there are three types of shear failures. So let me draw that once. Yes. Okay. So there are different modes of a shear failure. Now let's see one by one what are the different modes of the shear failure. Number one, general shear failure. Number two, local shear failure. And number three, punching shear failure. So general shear failure, local shear failure, and punching shear failure. So these are the type of different type of the failures that we are going to see. And now one by one, look, I told you yesterday, see, this is not a simple consolidation or a settlement or shearing. It's a combination of everything. When you apply some external load, you know that first the soil will undergoes compression. First, soil will undergoes compression, and then due to the shear stress developed, there is a shearing. So when an external load is applied, due to that external load, there is a normal stress, consolidation, settlement. There is a shear stress, shearing, shear failure is going to be there. So now what is the meaning of this general shear failure, local shear failure, and punching shear failures? Let's come to one by one. This general shear failure is going to be seen in low compressible soils. In the case of low compressible soils. So example, dense sand, stiff clay. And local shear failure can be seen in medium compressible soils. Example, medium sand and clay. And this punching shear failure is going to be seen in a very high compressible soils. Very high compressible soils. So here the example is going to be loose sand and soft clay. Loose sand and soft clay. So these are the different type of failures that we are going to see. First, let me write down the points, then I'll show you the figures also according to that. So low compressible soil, and this general shear failure occurs when ID is going to be greater than 70%. What is the meaning of ID? Relative density. ID means relative density. I hope you remember the relative density topic. ID, which is going to be E max minus E by E max minus E minimum. There I told you the ranges also. When ID greater than 70%, I told you ID 65 to 85% dense, and more than 85 highly dense. So that's the reason why I say it as a dense soils mass. And here the relative density, in this case 30% less than ID less than 70%. So 30% less than ID less than 70%, which means medium range. And in this case, ID is going to be less than or equals to 30%. So as I told you, if the ID value is going to be decreases, the denseness of the soil mass is going to be less, and they are going to be highly compressible soils. Okay. So now, in this case, the angle of internal friction is going to be phi greater than 36 degrees, and here phi is going to be less than 28 degrees, and is going to be angle of internal friction phi is very less. So now what is the meaning of this one, sir? What is the meaning of this one? So now let me show in the pictorial representation. If you observe, in the case of the general shear failure, number one, general shear failure. We represent this general shear failure as GSF. So you see, in the case of the general shear failure, whatever the figure I represent, this is general shear failure. Earlier, this is the footing. Earlier, this is the footing. Now, what happens is, when the load is going to be applied, the footing is going to be, first of all, the soil below the footing will be under compression. The soil below the footing will be under compression. And slowly, what happens is, on one edge, the soil starts to tilt. On one edge, the soil starts to tilt. You see, the soil starts to tilt, right? Then the footing is going to be displaced like this. And when the footing is going to be displaced, now you observe this entire soil mass. Have you remembered the Rankine's theory is earth pressure, active state, passive state? When the wall moves towards the soil, that is going to be passive state or not? Now you see, this entire soil mass will move downward and outward. This is nothing but downward and outward, and you can see a huge heaving at the ground level. See, this is the ground level, Nana, and this is a ground level. You can observe in the case of the general shear failure. General shear failure occurs in whom? Low compressible soils. At first, the soil will undergo less compression. Less compression means settlement is going to be less. Settlement is going to be less. Then this soil mass will move downward and outward, causing a bulging or heaving at the ground surface. So this type of failure, you can observe, this is a footing. The footing is going to be tilt. Then the entire soil mass, the below soil mass will undergo compression, and the side mass will be under the shear. So this is the side soil mass which is under the shear. So now this will happen, sir. Why you take on the left side? Why can't I take the right side? It can be happen in one side, or it can be happen in both the sides also. So now the same figure I'll be represented in this fashion. Have a look. Yes. So if you observe, what happens over here is, at first the soil will start to tilt. So in this zone, the soil will move like this. Okay, means the footing is going to be tilt. The footing is going to be tilt, and it starts to rotate up to the ground surface. Up to the ground surface, leaving. See, when this footing is going to be deviate in this manner. See, this is initial position, and this is the final position. There is a heaving at the ground surface, and this is one side. Similarly, there is a one more side. So this is one more side. See, here I am representing one side. Now here I am representing both sides. Yes or no? And as it is going to be general shear failure, my dear students, you tell me, in the case of the general shear failure, as it is a low compressible soil or high compressible soil, low compressible, then the settlement of the soil is going to be very, very less. So whatever this is nothing but, let's take it as a S1. What is meant by S1? Settlement. So number one, general shear failure. In the case of the general shear failure, from this figure, I can say it's a well-defined failure plane having bulging at ground level, and there is a sudden failure, ground level with a sudden failure. Okay, so now coming to the local shear failure. Well-defined failure plane having a bulging at the ground surface with a sudden failure. So now coming to the second one, local shear failure. In the case of the local shear failure, now if you observe here, the soil below the footing comparatively, if you observe, please look over the condition clearly. Comparatively, this is the footing settlement, right? S1. Now comparatively, the footing has been settled to this position. The footing has to be, the footing has settled from here to here. Yes or no? So my dear student, you tell me, the local shear failure is going to be happen by more compression below the footing. More compression below the footing, which means medium compressible soil. So compared to the general shear failure, you see the tilting of the footing here, there is a more compression, and mind it, the movement is going to be less. The movement is going to be less. Here, side soil will undergo more shear. In the case of the general shear failure, soil below footing has less compression, and soil shear more in sides. But in the case of the local shear failure, soil below footing undergoes more compression and partial shear in sides. See, this is a side soil, right? This is a side soil, and this is going to be soil below the footing. So now you see, is there any objectionable heaving here? No. Here in this case, if you observe this slip surface, whatever, this is nothing but the failure plane or failure surface. See, in the case of the local shear failure, the failure surface will not extend up to the ground level. So here, this is a well-defined failure plane with no sudden failure. So with no sudden failure means no heaving. If there is a sudden failure, then there is a heaving, having a bulging or heaving. So in this case, if I draw the figure, so here there is no bulging. There is no bulging over here. But what happens? As I told you, the soil below the footing undergoes more compression. Yes. So the soil below the footing will undergoes more compression. So compared to the general shear failure, whatever the soil below the footing undergoes more compression. Let's take this magnitude as S2. Means in the case of the local shear failure, and the shearing is going to be happen up to the base of footing only. Up to the base of footing only. Look, in the case of the general shear failure, the shearing is going to be happen up to the ground surface, right? But in the case of the local shear failure, local, so the shearing is going to be mobilized locally. Shearing happens locally, which means a partial shear. So the basic difference between the general shear failure and local shear failure is, in the case of general shear failure, you see the failure reaches up to the ground surface with a huge heaving. And in the case of the local shear failure, you can see there is a small tilting, but there is no heaving on the ground surface on one side. Similarly, on the other side. Similarly, on the other side also. So I hope you understood the difference between the general shear failure and local shear failure. So in general shear failure, low compressible soils, here high compressible soils. Sir, how come you say low compressible, sir? So ID more than 70, here ID is going to be in between 30 to 70. You know the ID means relative density. And generally when phi greater than 36 degrees, general shear failure, phi less than 28 degrees, that is going to be punching shear failure. Sorry, local shear failure. Now coming to the last one, punching shear failure. You see the third one. This is punching shear failure. So in this, soil below footing is heavily compressed with no shear on sides. With no shear on the sides. So you see here the moment is going to be completely vertical. And you see this is a vertical shear. This is a vertical shear. Is there any movement on the side? No, no movement on the side. As there is no movement on the side, this type of failure is known as a punching shear failure. My dear students, this failure will occur only in the case of highly compressible soils. I hope you know the highly compressible soils means loosest soils are not. In the case of loosest soils, what type of foundations we prefer? In the case of the foundations, means loosest soils, what type of foundations we prefer? Pile foundations. We prefer pile foundations. So now, if you see the same figure, so instead of that figure, I will be going with the pile foundation now. So this is a pile. And now, in the case of the pile foundation, if you observe, when you apply load, so here the soil will undergo continuously the settlement, vertical settlement only. So this is known as S3. There is no side shear at all. There is no side shear at all. So this type of failure is known as a punching shear failure. This type of failure, local shear failure up to the base of footing. This is going to be general shear failure up to the ground surface. I hope you understood over here. So in this case, no well-defined or poorly defined failure plane, poorly defined failure plane. So at last, this type of failure can be seen in the case of shallow foundations, and this is also going to be seen in the case of the shallow foundations, And here, this is going to be seen in the case of the pile, or I can say directly deep foundation, means pile foundations. So you see, my dear, these are the different points, and these points are very, very, very important in the case of ES examination. Please have a look. I'll show you the figures also. First, you please have a look over here. And if you understand this, and you can get to know everything in the figure itself. Sir, if phi is going to be lies between 36 degrees, if phi is going to be lies between 36 degrees and 28 degrees, then we call it as mixed shear failure. But we don't discuss about the mixed shear failure much. We don't discuss about the mixed shear failure much. So don't worry about the mixed shear failure. Yeah. Well defined means, you see, the failure plane is going to be clearly seen or not. So that's the reason why we can say it as well defined. And here there is no failure plane. You can see, can you see the failure plane of a soil mass? No. I hope you understood this. Now, for all these three, I am going to draw a figure: the general shear failure, local shear failure, and punching shear failure. So now, in x-axis, I am going to apply the gross pressure, and in the y-axis, I am going to see the settlement. See, you know, whatever, this is nothing but the gross pressure at the base of the footing. This is nothing but the backfill or not. So there is some gross pressure, and this is known as a gross pressure. So my dear students, please observe over here. So my dear student, if you observe over here, for the same peculiar pressure I applied, the general shear failure settlement is going to be less than the local shear failure than the punching shear failure. Which settlement is going to be more over here? S3 is more than S2 is more than S1. So now for the corresponding pressure and settlement, if I draw the graph, first I told you the general shear failure is a well-defined failure plane with a sudden failure. With a sudden failure. With a sudden failure means, now you see, look at the point of time. If you observe here clearly, if you see, look, the slope of this curve is going to be very less. Yes, as a Q increases, settlement increases, but at what rate? Very, 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 very less rate. So in the case of the general shear failure, as it is a low compressible soil, settlement is going to be less. And once suddenly it is going to be fail like this. Suddenly the failure is going to becomes like this, and this is the failure. And if you see, this is nothing but a sudden failure or not. So due to this sudden failure, we call this one as whatever this curve is going to be general shear failure, because you can see the failure plane and there is a sudden failure. And up to this point, the settlement was less and suddenly the settlement is going to be more. This type of failure is known as general shear failure. Let me draw the failures once again. Then you can go for the all those figures. So, and then the failure can be like this, or the failure can be like this also. So now, my dear students, what I am asking you is, at a particular stress, now if I drop a vertical line, if I drop a vertical line, now if you observe, you see, this is the settlement on the graph 1. This is the settlement on the graph 2. This is the settlement on the graph 3. So I hope you observe over here, whatever the settlement, this is going to be S1. And whatever the settlement is going to be S2. And whatever the settlement is going to be S3. So which settlement is going to be more? S3 is more. Whenever the settlement is going to be more, I told you, if the soil is heavily compressed, such a type of failure is known as a punching shear failure. This is known as a punching shear failure. And less compression with a sudden failure, you see sudden failure, clear progressive failure, then this type of failure is known as a general shear failure. And now in between, if you observe, in the case of the in between, this is going to be local shear failure. So my dear students, from these points, settlement is less in the case of GSF. Yes, settlement S1 is less, and that is going to be GSF. And settlement is going to happen easily. You see, with a small pressure also settlement is more, then the soil is very loose. Such a type of failure is known as a punching shear failure. So these are the graphs which represents the variation of the gross pressure versus settlement for various failures. And mind it, all this has been conducted, this test has been conducted on the whatever strip footings only. See, these are the model test. By conducting model test on strip footing. See, this is a strip footing, Nana. Whatever I am showing you is a strip footing. So by conducting model test on the strip footing, if the tilting is going to be there and there is a heaving, general shear failure. And if there is a small tilting but there is no heaving, local shear failure. And if the footing is going to be exactly punches below, then you are going to call it as a punching shear failure. So with this, whatever that discussion regarding to the concept and the theories is going to be done. Now let's see how to design. Let's see how to design. So the design means determination of ultimate bearing capacity. QU means ultimate bearing capacity. This is nothing but gross pressure. Okay. So determination of the ultimate bearing capacity. Now let's see. You know that the design condition is simple. What is the design condition? I have said you, Q less than or equals to QS. So the design is yet failure Q is equals to QU. Sir, what is the meaning of the QU, sir? Yet failure Q is equals to QU. What is the meaning of QU? Come on, tell me the definition of the QU. Let's go back. Yeah. See, look over the definition of QU. Maximum gross pressure that a soil can bear without any shear failure. Which means, can I say, yet a failure, whatever the pressure you applied is nothing but the ultimate bearing capacity or not. For example, my ultimate bearing capacity is 200. My ultimate bearing capacity is 200. And what is the maximum gross pressure you apply? 200 only, right? If you go more than 200, my capacity is 200. If you apply a gross pressure of more than 200, then I am going to be failed. So at the verge of failure, whatever the gross pressure you applied will be the ultimate bearing capacity. So now, at a failure, Q is equals to QU, and for safe condition, Q should be less than or equals to QS. So if I say failure, Q is equals to QU. And if I say safe condition, Q should be less than or equals to QS. Mind it, my dear students, we are an engineers. When we analyze, the analysis is for the critical condition. When we design for the safe condition. See, we go for analysis as critical and we check, okay, this is the point where the soil is going to be fail. But while we design, we have to design safely, right? So now, how to determine the ultimate bearing capacity? So again, there are some theories. First, Rankine's theory. So I hope you remember the Rankine's theory, everybody. I hope you remember the Rankine's theory. In chapter number 14, same assumptions are going to be useful here also. Soil is dry and cohesionless. Soil is dry and cohesionless. See, soil is dry and cohesionless. Where? In the case of the Rankine's theory, there also in chapter number 14, Rankine's earth pressure theory, soil is dry and cohesionless. Their back of wall is going to be smooth. Their back of wall is going to be smooth. Here, base of footing is smooth. And now you tell me, look, my dear students, according to Rankine's, there are two states, active state and passive state. What is meant by active state? What is meant by active state? Active state means when the wall moves away from the backfill, active state. Wall moves towards the backfill, passive. Now, instead of wall, I am taking the base. So now, when you apply the load, does the wall is moving towards the backfill or away from the backfill? Wall or footing is moving towards the backfill. When the footing is moving towards the backfill, you see, when the footing is going to be moving towards the backfill, is it a passive equilibrium or active equilibrium? Passive state. So, in the case of the footings, as the footing moves towards the soil reaches passive plastic equilibrium condition. See, I told you what is the meaning of the plastic equilibrium. What is the meaning of plastic equilibrium? At every point in the soil mass, it will undergo shear failure. That is known as a plastic equilibrium. Passive plastic equilibrium condition exists. So this is the Rankine's theory, and according to Rankine's theory, what he said is, whatever the gross pressure I apply, that is going to be gamma into D into Kp square. Gamma into D into Kp square. See, don't worry about the derivations over here. You don't look over the derivation. So if you construct a footing, if you construct a footing, whatever the pressure that is going to be applied, Yes. Yeah. So if you construct a footing, whatever the pressure that is going to be applied, that pressure, the maximum pressure is going to be like gamma d into Kp square. And you know that at a failure, Q is equals to Qu, means ultimate bearing capacity. At failure, ultimate bearing capacity. Then Qu is equals to gamma d into Kp square. So what is meant by Kp, sir? Coefficient of passive earth pressure. Coefficient of passive earth pressure. But there is a disadvantage over here. The limitation in the case of the Rankine's theory, the limitation is at ground level, which means D is equals to 0, then Qu is equals to 0. See, at the ground level, if you observe over here, at the ground level means D is equals to 0, then according to the Rankines, Qu is equals to 0. Is it going to be possible? Is it going to be possible? See, what is the meaning of ultimate bearing capacity? The ability of a soil mass to take the stress without any shear failure. Yes or no? That's it, right? What is the ability of a soil mass? The pressure that a soil can take without any shear failure. Are Baba, if the ground level, at a ground level, if ultimate bearing capacity is 0, then can we walk on the soil? When we walk, we are going to apply the shearing or not? When we walk, we apply shearing along the plane. If I say at the ground level D0, then ultimate bearing capacity 0. Is it going to be possible? No, which is not going to be, which is not possible. This is the biggest limitation of this Rankine's theory. That is the biggest limitation of the Rankine's theory. And sir, then what about this Rankine's theory uses, sir? This Rankine's theory is going to be used. This Rankine's theory is going to be used to determine the minimum depth of the foundation. So for this, the D minimum is equals to Q by gamma into Ka square. As you know, Ka is equals to 1 by Kp. And you know that Ka is equals to 1 minus sine phi by 1 plus sine phi. So in the case of the Rankine's theory, the limitation of the Rankine's theory is, at a ground level, this theory is not going to be applicable. At a ground level, this theory is not going to be applicable. So that's the reason why we use the Rankine's theory to determine the minimum depth of the foundation. What is meant by D? D is nothing but the depth of foundation. What is meant by D? D is nothing but the depth of the foundation. So where D, depth of foundation. So that's about the Rankine's theory. Now there comes our Father. Wherever you go, our Father will come and he keeps all his fingers and legs in this. So now let's see the major, see out of all the theories I'm telling, see my dear students, if you look over the textbooks, there are a lot of theories I'm telling you. There are some empirical theories, there are some analytical theories. So there are lots and lots of theories. I can say that Prandtl theory, Hensel's theory, and Meyerhoff's theory, Kempton's theory, Terzaghis theory, IS code method, n number of methods are there. But for the GATE examination and for the IAS examination, the most important method Repeating the point, the most important method is Terzaghi's method. So now, first, stop everything and start listening. Terzaghi's theory. So this Terzaghi's theory, this is a modified version of Prandtl. Prandtl is also a scientist, modified version of a Prandtl theory. Mr. Shashikant Terra, what I have to respond here? What I have to respond? So respond means what I have to respond. So now coming to the modified version of the Prandtl. So in the case of the modified version of the Prandtl, now for every theory there must be some assumptions, right? So this is suitable for means soil fails by general shear failure. See, let's first write down the assumptions made by the Terzaghi. Then we discuss about the remaining things. So the major assumption made by Terzaghi is the soil fails by general shear failure. And base of footing is rough. Base of footing is going to be rough. Yes, it's going to be Terzaghi only. So soil fails by general shear failure. Base of footing is going to be rough. And apart from that, see, these are the basic things. Apart from that, you take the footing. So far and so good. Whatever the shallow foundations I discussed, you see, am I considering anything regarding of this soil mass above the base of footing? No. So whatever the soil mass above the base of footing is just considered as surcharge acting at the base of footing. First, let me write down all those things. So soil above base of footing is considered as surcharge acting at base, which means in simple words, side resistance is neglected. So side resistance is going to be neglected. So as I said, that's going to be side resistance is going to be neglected. Then we can say this is going to be suitable for shallow foundations or not. See, I can make sure all the points. Soil fails by general shear failure, and you know that general shear failure occurs in what type of foundations? Shallow foundations. And one more thing, in the starting itself, I told you. In the starting itself, I told you here. In the case of the shallow foundations, side resistance is going to be neglected. So, which means this is suitable for shallow foundations. This is suitable for the shallow foundations, and as the soil is moving towards the backfill, means towards the, as the wall is moving towards the soil, passive plastic equilibrium condition exists. Passive plastic equilibrium condition is going to be exist. Now let's draw the failure planes. So let's see, based upon these things, soil fails by shear. Yes. Base of footing is going to be rough, and soil above the footing is going to be considered as a surcharge acting at the base. So now let's draw the figure. So this is the footing. As I told you, this is going to be suitable for whom? Shallow foundation. So now this is going to be the ground level. So if this is the case, now let's see the point number 1. If you observe, so point number 1, you see soil above the base of footing. Whatever, this is nothing but the depth of foundation. Let's take the depth of foundation as a D. So whatever the soil above the base of footing is considered as a surcharge acting at the base. So whatever here, we are going to consider this as a surcharge at the base. See, if you keep your pump, what is a surcharge? You can feel gamma into D. See, don't take this Q as a gross pressure. This is surcharge. This is going to be surcharge. So what is side resistance, sir? Now you see the side resistance. See, look, the side resistance is going to be, you have a look over here. Now, whatever the resistance over here in the side, this is known as a side resistance now. But in the case of the Terzaghi, you are not going to be considered the side resistance. So there is no resistance in the sides. The resistance is going to be happen only in the base. Now, according to Terzaghi, what is the type of failure? General shear failure. So how the general shear failure is going to be looks now. You see, this is a portion which is going to be the soil portion below the footing, and now there is a failure. And this failure will be a plane like this. You see, this is one side, and mind it, I am not taking anything above. Because above the side resistance is going to be neglected or not. That's what the meaning. Side resistance is going to be neglected. So now as I am going to neglect the side resistance, I don't take any resistance above. Now similarly, similarly, you see the same thing on the both sides. So if you observe over here, first of all, my dear student, you see, if this is the B is the base of the foundation, and this shearing is going to be happen. This is known as a shear zone. Whatever this is known as a shear zone, and this shear zone is going to be happen up to a depth below the ground level as so whatever the depth below the ground level, this depth is going to be exactly same as the width of the footing. So if B is the width of the footing, see, the B is the width of the footing, and exactly below the width, the shearing is going to be happen. And still, Now, what is going to be happen over here, sir? Sir, now if I apply the load, at first, I'm going to divide into this into 3 zones. On one side, first zone, second zone, and this is going to be third zone. And again, second zone, and here it is going to be third zone. So what are these zones? So can you please explain us one by one? So let's see that zones. Zone number 1, zone of elastic, or I can write that as elastic zone. Elastic zone. So in the case of the elastic zone, soil below footing is compressed and prevented from any lateral movement. Prevented from any lateral movement. You see, movement means here as a movement. Movement. You please observe over here. See, this soil will try to slide like this, and this soil will try to slide like this. Now, as it is under compression, this rotation or movement will be contracted by this moment, and this movement is going to be contracted by the other movement, which means if the soil tries to move like this, the other soil tries to refrain or restrain. If the other soil moves, then this soil is going to be restrained, so that there is no lateral movement. When there is no lateral movement, soil will be which state? Elastic state or plastic state? So acquires or attains elastic equilibrium. Elastic equilibrium. Now, this is zone 1. Similarly, zone 2. This is known as radial shear zone. Radial shear zone. So now, my dear students, you please observe. Once it crosses this point, this is going to be a triangular wedge, right? This is going to be a triangular wedge. And now, in the case of the elastic zone, the soil and the footing are going to be act like a single member. The soil and the footing is going to be actually like a single member, because as a base of the footing is going to be whom? Rough. Due to the base of footing is going to be rough, the soil mass, due to the friction and adhesion between the soil and the wall, they are going to be acts like a rigid member. They are going to be act like a rigid member. So zone 1 is elastic zone, and from this point onwards, actually the soil starts to shear. Actually the soil starts to shear, and there is a resistance along the shearing. See, whatever, this is nothing but shear resistance. So there is a resistance along the shear. Now this is known as a radial shear. Mind it, I am showing you only 2-dimensional. I am showing you only 2-dimensional. So along the width, this is, and along the length also there is there or not. Just imagine this thing in 3-dimensional. In all the radial directions, there is a shearing. So that's the reason why we call it as a radial shear zone. Shearing of soil occurs in all radial directions. Now, zone 3, passive zone. Passive zone. So what is a passive zone, sir? While shearing, soil attains plastic equilibrium and fails, making an angle of 45 minus 5/2. See, you know that soil is not going to be filled directly. First, the soil below the footing is elastic, and then slowly the shearing is going to be start, and then as the shearing happens at one point of time, it attains the plastic equilibrium or not, then the soil is going to be filled. And you know, you see below the footing the soil is under passive state. Now you observe whatever the angle made by the failure plane with respect to horizontal in passive state is a 45 minus 5 by 2. 45 minus 5 by 2. I hope you understood this. 45 minus 5 by 2. So if this is going to be 45 minus 5 by 2, then this angle is going to be 5. So I am not going to discuss about why this 5 came. You please resolve these components. 45 minus 5 by 2, then he is going to be the remaining the values. If you do proper mathematics, then you can get the 5 value. So in the case of the active state, 45 plus 5 by 2. And in the case of the passive state, 45 minus 5 by 2. If you have any doubt, please go to the chapter number 14. There I have been discussed. While shearing, soil attains a plastic equilibrium and fails, making an angle of 45 minus 5 by 2 with respect to horizontal. So these are the zones: radial shear zone, passive zone, and I have used all the assumptions made by the Terzaghi, and based upon these assumptions, he explained for a strip footing. For strip footing, I am not going to show the derivation, please. I am not going to show any derivation for the strip footing. The ultimate bearing capacity is given as CNC plus, you see, at the base of footing it is going to be acts like a surcharge or not? Surcharge QNQ plus see below the footing, this is nothing but a shear zone. Yes. So whatever the soil mass below the footing, there is under shear zone. Now here plus 0.5 gamma B and gamma 0.5 gamma B. You see, my dear student, at the base of footing, what is surcharge? Gamma D. Below, what is the depth we are going to take? B. And what is the self weight? You can see here below the base of footing. You see below the base of footing at a depth B, what is the self weight? Gamma into B. Gamma into B. Keep that in your mind. The effect that we are going to take is up to this depth. The effect that we are going to take is up to the total depth D plus B only. We don't consider anything beyond this B. So this is known as gamma B. First of all, what is meant by C? Cohesion. The cohesion is going to be present all over the soil, and then surcharge Q, and then gamma B. Gamma B means the effect of the soil mass in the shear zone, means soil under shear. So this is the equation that given by the Terzaghi. But what I do is I divide this into 3 zones. So what are those 3 zones, sir? Number 1, cohesion effect. Number 2, surcharge effect. Number 3, width effect or effect of soil in shear. Effect of soil in shear. So these are the equation given by the called Terzaghi to determine the ultimate bearing capacity. QU means ultimate bearing capacity, where see I am not going to remember this equation as a whole. I divide into 3 parts. What are those 3 parts? Number 1, cohesion effect. C, surcharge. Q, width, gamma. B, R, effect of the soil in shear. Whatever the effect of the soil in shear. What is the effect? This is a shear, right? This is in a shear zone. So whatever the soil in the shear is nothing but gamma into B, and keep that in your mind. Whatever this point for, this is nothing but shape. For what type of footing I am using? Strip footing. So QU is nothing but CNC, cohesion effect, plus please try to remember as a individual components, not as a total component. Three components are there: cohesion, surcharge, and width or shear. So cohesion CNC, surcharge Q, NQ, and width effect gamma, B and gamma. So now where NC, NQ, N gamma, sir, then what is this NC, NQ, N gamma, sir? That NC, NQ, N gamma are bearing capacity factors. What is that? NC, NQ, N gamma are bearing capacity factors. Where NC, NQ, N gamma are bearing capacity factors that depends on angle of internal friction. Angle of internal friction. Keep that in your mind, my dear students. You don't need to worry about remembering NC, NQ, N gamma. Actually, this NC, NQ, N gamma is a function of phi. There is some equation with respect to the phi. But for your UG level, undergraduation level, you don't require those equations. NC, NQ, N gamma. I'm not going to discuss those equations also. So don't worry about that. There is a derivation behind this, but don't look into that. You don't need to worry about those. In the examination, then what to do, sir? In the examination, they will provide you NC, NQ, N gamma, sir. I'll show you the question. Yes, if you observe this question, for phi is equal to 30 degrees, NQ and N gamma. See, means NC is also there, but the soil mass is going to be sandy soil. So the phi value means the NC, NQ, N gamma value depends upon phi. So what is mean by NC, NQ, N gamma? The meaning of NC, NQ, N gamma is bearing capacity factors, which depends upon the phi value. So keep that in your mind. These are depends upon the phi value, and there is a C usage, there is a phi usage, there is a gamma is there, there is surcharge is there. So I hope you remember these are three effects. And once you know the QU, then what is QNU? Net ultimate bearing capacity is nothing but ultimate minus gamma D. Then what is the net safe? Net ultimate by factor of safety. Then what is a safe? Net safe plus gamma D. And design condition. What is design condition? I have given you. The design condition is Q less than or equals to Q. Yes. See, all these things we discussed earlier. If you want to design, sir, what is the design, sir? If you want to design the width of the footing, depth of the footing, factor of safety for the footing, then you have to use this condition only, Q less than or equals to Q. Yes. And for finding all these things, you require the ultimate bearing capacity. And this equation is given by the Terzaghi for what type of footing? Strip footing. Now let's see some conditions. With this. These are the most interesting conditions over here. The conditions are, so if you observe the conditions, number 1, for clay soils, for the clay soil, so if the soil is a clayey soil, then its a phi is equals to 0 degrees. Its a phi is equals to 0 degrees. When phi is equals to 0 degrees, then NC has two values again. Those values are, one is 5.7 other one is 5.14. Those values are, one is 5.7, other one is 5.14. So this is going to be there when base is rough. When base of footing is rough, we are going to use 5.7, and when the base of footing is going to be smooth, when base is smooth, we go for the 5.14. Okay, fine. Okay, so some of the students want, so please change the slide. Yeah, I change the slide. Please look. Where is that? Please change the slide. I hope you understood. And now, okay. See, in the case of the base of footing is going to be rough, sir. When do you use base of footing rough, sir? According to Terzaghi, and this is according to Prandtl. As I told you, you see, observe, Terzaghi series is a modified version of the Prandtl. What is the difference between the Terzaghi and Prandtl is, Terzaghi assumed base of footing is going to be rough, whereas the Prandtl assumed base of footing is going to be smooth. See, now in the case of the clay layer, in the case of the clay soil, you have to remember these values. When 5.0, then NC is equals to 5.7 or 5.14. When it is going to be 5.7, base of footing is rough. When it is going to be 5.14, base of footing is going to be smooth. Keep that in your mind. In the examination, they will ask you using Terzaghi. When I mention Terzaghi, base of footing is going to be rough. When base of footing is going to be rough, then the NC value you have to use it as a 5.7. And if I mention clearly, sir, base of footing is going to be smooth, then you have to take NC as a 5.14. I hope you understood. So this NC value depends upon whom? Base. And then NQ is equals to 1 and N gamma is equals to 0. See, you need to remember these values. There is no option. You have to remember these values. Sometime in examination they will give, and sometimes they won't give also. So you need to understand these values. So once I know for the clay soil mass, when phi is equals to 0 degrees, then NC, NQ, and gamma. Now, write down the equation. What is ultimate bearing capacity? You please write down as many times as possible. CNC plus, now I can write the surcharge. Can I write the surcharge as gamma into D? Yes, because you know the surcharge is nothing but gamma into D here. So now CNC plus gamma D NQ plus 0.5 gamma B and gamma. 0.5 gamma B and gamma. Now you see N gamma is going to be 0. NQ is equals to 1. See, when N gamma is equals to 0, now what is the QU value? You see CNC plus gamma D. So I did not apply NC value because it depends upon the base of footing, whether it is rough or smooth. Based upon that I can take. Now my dear student, if you observe carefully in this condition, is there any width effect? Is there any width effect? So now you see, I have given this one in terms of 3 effects. Width effect, yes or no? Now, in the case of the clay soils, N gamma 0 means width effect is going to be neglected. Width effect is going to be neglected. So with this, can I write in clays, the ultimate bearing capacity is independent on width of footing. Sir, why it is going to be independent on width of footing, sir? Now you see, sir, what is QU, sir? In the case of the clay soils, what is QU, sir? Cohesion effect is there and surcharge is there. But where is the width, sir? Whether the width is 1 meter or 2 meter or 3 meter or n meters you take, the ultimate bearing capacity of the clayey soils is independent on width of footing. Keep that in your mind because n gamma is going to be 0. So now once you know this, you know that net ultimate bearing capacity is nothing but QU minus gamma D. So now if you write, then what is QNU? QNU means CNC plus gamma D minus gamma D. So with this gamma D and gamma D will get cancelled down. Then what is the net ultimate bearing capacity of soil in the case of the clays? CNC. So cute, right? The only equation in the case of clays, what is net ultimate bearing capacity? Cohesion effect. Say I have three effects. Cohesion effect, depth effect or surcharge effect, and width effect. In the case of clay, width 0. There are two effects. NQ is equals to 1. That's when you go for the net ultimate bearing capacity, then surcharge is also gone. Then what is the only effect? Cohesion effect. So in the case of the clay soils, you have to remember this. So what is the net ultimate bearing capacity of clay soil? CNC. And what is NC? 5.7 according to Terzaghi, 5.14 according to Prandtl. Why is that? Base is smooth and base of the footing is going to be rough. So this is about the clayey soil mass. Now for various footings, shapes of footing. For various shapes of footing. See, I take only one equation. This is the equation I am going to use. I don't remember too many equations. I'll remember only one equation. You please look over this equation only. And based upon this equation only, I am going to change everything. See, this footing is going to be strip footing, right? As it is going to be strip footing for various footings. You know that in the case of shallow foundation, there are different type of footings. So in the case of those, they have some shapes. It may be rectangle, it may be square, it may be circle. Yes. First. Circular footing. So if the footing is going to be circle, then what to do? What to do? What not to do? Now you see QU, whatever you know, you write. First of all, you write whatever the equation you know. That's it. You write the equation, whatever you know. And then later on, I'll see the modification. What is the equation I know? CNC plus gamma DNQ plus gamma B and gamma. So my dear student, I told you this 0.5 is going to be shape factor, right? So now this is the equation that we know. This is the equation that we know for whom? Strip. Now when I change that strip shape into circular, now you see due to this the cohesion is going to be increases by 30%. The cohesion is going to be increases by 30%. When the cohesion is going to be increases by 30%, then there is going to be 1.3 CNC, whereas the shape factor, whatever this is nothing but it is no more 0.5, it is going to be 0.3. You please observe the change. Here I change it to 1.3, here I change it to 0.3. I'm telling you again, you don't look into the derivations. Even for ESC mains also, they won't ask the derivations. So don't worry about that. Even in your BTech level also, they won't ask the derivations, Nana. The derivations are important in the case of the PG, post-graduation. So there you are going to learn all those things. So don't worry about that. So instead of focusing on what is not necessary, it's not 1.3% rate, it's 1.30% increase means 1.3, right? 20% increase, 1.2. So now, in the case of the circle, it is going to be gamma d NQ, and there is no change in the gamma d. Why, sir? Why there is no change, sir? Sir, that is surcharge, sir. That is surcharge, sir, and that is above the footing, sir. See, if the shape of the footing changes, why the above the footing will change? Whatever the soil must below the footing will change, but not above the footing. So now, in the case of circle, 1.3 CNC plus gamma DNQ plus 0.3 gamma B and gamma. Similarly, second one, square. Come on, don't you write whatever you know, that's it. CNC plus gamma D NQ plus gamma B and gamma. Similarly, in the case of the square also, cohesion increases by 30%, 1.3, whereas a shape factor is going to be 0.4. See, in circle, the shape is going to be 0.3, means the value of coefficient. In the square, it is going to be 0.4. And in the case of strip, it is going to be 0.5. You keep that in your mind, 0.3, 0.4, 0.5. 0.3 for circle, 0.4 for square, 0.5 for the strip. See, I don't want to remember too many formulas. See, if you want to remember circle has different formulae, square has different formulae, gone. So do remember the equation as 3 parts: cohesion, surcharge, and width effect. No effect on the surcharge, but in the cohesion, 30% increase. Whereas in the case of the width effect, 0.3 for strip, 0.3 for circle, 0.4 for square, and 0.5 for strip. And the last one is rectangle. In the case of the rectangle, let me write down the equation directly. QU is equals to 1 plus 0.3 B by L CNC plus gamma D NQ plus in the case of rectangle, QU is equals to 1 plus 0.3 B by L into CNC plus gamma D NQ plus 0.5 into 1 minus 0.2 B by L gamma B and gamma. So this is the final equation in the case of rectangle. See, if you just observe the rectangle and square, when do you call square? When B by L is equals to 1, that is going to be square or not? You just look over here. If I write B by L as 1, if I write B by L as a 1, then for B by L 1 plus 0.3, 1.3, no change in the surcharge effect, plus 1 minus 0.2 B by L. B by L means 1 minus 0.2, 0.4. Sorry, 1 minus 0.2, 0.8. 0.5 into 0.8 is going to be 0.4. So I hope you understood the points over here. So the equation is going to be one equation, but you need to look over what is the changes. Here, this is the change. Here, that is the change. So if you are able to understand these changes, then you don't need to worry about remembering too many formulas. So this is for various shapes, and this is for that different type of soil. Let me show a question. Yeah, you see this question. This is a previous ESC question. Two circular footings of diameter D1 and D2 resting on a surface of a purely cohesive soil. So given is pure clay. Given is pure clay. The ratio of D1 by D2 is equals to 2. Okay. If the ultimate load carrying capacity, see that D is the diameter over here of footing. Okay. So see, in the case of the circle, let me go for that once again. In the case of the circle, this B is nothing but dia of footing. That B is going to be nothing but whom? Diameter. This is nothing but a diameter, Nana. Somebody is asking, sir, why Q is independent on the width of footing, sir? Now you see, sir, is there any width component, sir? No, sir. That's the reason why Q is independent of width of the footing. Now, so dia of the footing. And now, in the case of the QU1 for D1, for D1, QU1 is equals to ultimate bearing capacity, ultimate load carrying capacity given as 200 kilonewton per meter square. Then the ultimate bearing capacity of D2, QU2 is how much? Just now I told you QU is independent on width or diameter of footing. So QU is going to be independent on width or dia of the footing. If it is a rectangular square width, 2 meters, 3 meters, 10 meters, the ultimate bearing capacity does not depend upon width. So whatever the width you take, its ultimate bearing capacity is same. But the given is circle, right? Having two different diameters. I don't care whether the diameter is 1 meter or 0.5 or 10 meters, the ultimate bearing capacity is the same. So the answer is going to be 200 kilonewton per meter square only. The answer is answer B. With a simple logic, I can find it, right? Because in the case of the clays, now if you want me to go for that equation, yes, this is the diameter equation, right? Means a circle equation. In the case of the clays, you know n gamma is 0. In the case of clays, you know n gamma is 0. If you keep n gamma 0, then the diameter means effect of the dia is going to be 0. So my dear students, in clays, width or diameter effect is going to be 0. Mr. Kalpesh Thakre, please explain compensated raft foundation. I have explained 20 minutes, and if you have came late, I'm not responsible for that. So you please go through the video once again. Now, yes. So you see this one. Now, I want to introduce one more topic over here. Larger footings settles more than the smaller footings under the same load intensity. Look. This is a small footing. This is the larger footing. Have you remember this is small footing and this is going to be larger footing. Have you remembered the pressure bulb concept? If you have remembered the pressure bulb concept, I told you the pressure bulb, if this is going to be B1 and if this is going to be B2, the pressure bulb is going to be, this is nothing but pressure bulb. Yes, the pressure bulb is going to be up to what depth? 1.5 to 2 times of B1. Similarly, here this is the pressure bulb. So whatever this pressure bulb, this depth is going to be 1.5 to 2 times of B2. My dear student, I told you, if you remember in chapter number 10, in Bosni's theory, I discussed about the pressure bulb. Pressure bulb is used in determining the calculations of settlement. Arey Papa, just imagine what is the meaning of pressure bulb? Soil which is under stress. Yes, 0.2 Q isobar, whatever the soil below means 0.1 Q isobar. This is nothing but 0.1 Q isobar, right? Yes. And you see, the more the pressure bulb, the more the settlement. The more the pressure bulb, the more the settlement. So under same pressure, more pressure bulb, more more settlements. The more the pressure bulb, the more the settlements. See, I explained this topic earlier itself. Now I'm utilizing the topic just simply. Yes, it applies for all the other shapes too. So now larger footing settles more than the smaller footing. Yes. Size of pressure bulb depends upon the size of footing. Yes. So the more the size, the more the pressure bulb. The more the pressure bulb, more the settlement. So larger the footing, more the pressure bulb, more settlements. A is true, R is true, and R is correct explanation of A. R is correct explanation of A. Now, let's see this question similarly. 4 square footings which are going to be having a side B by B, each carrying a load intensity of Q, are spaced close enough. See, this is one footing, this is one footing. They are going to be provided with a very less footing space. Then, as shown in the figure, the significant depth. What is the meaning of significant depth? This is nothing but the significant depth, right? Whatever, this is nothing but the significant depth. So you know that significant depth is nothing but depth of the pressure bulb. So now, if I draw the pressure bulb for all the footings, this is going to be the pressure bulb. And whatever the depth, this is known as a significant depth. And this significant depth is nothing but 1.5 to 2 times of what is the total width? B. What is the total width? B. Don't ask me, sir, why you have not taken small. If you take smaller, then there is a portion of overlap like this. So that overlap leads to the C. Keep that in your mind. When the footings are too closer, you have to take the total pressure bulb. This is the total pressure bulb. And you know, the depth of the pressure bulb is known as significant depth. If you have any doubt, chapter number 10, Bosni's theory, there I have explained it clearly what is significant depth. And so that significant depth is going to be 1.5 to 2 times of B. And here the answer from the given options is going to be answer as D. Okay. Yes. Now you see 2 footings. One is circle. Other one is going to be square. 2 footings. One is circle. Other one is going to be square. So the other one is going to be square footing. Okay. Now are founded on a surface of a purely cohesionless soil. What is the meaning of cohesionless soil? See, the given statements are given cohesionless soil. What is the meaning of cohesionless soil? C0. See, keep that in your mind immediately. You know the ultimate bearing capacity of the soil mass is 3 components: cohesion effect, surcharge effect, and width effect. Cohesion effect, surcharge effect, and width effect. See, if I say cohesionless soil, C0, cohesion effect is going to be gone. And the dia of the circular footing is same as that of the side of the square footing. See, are founded on the surface. So footing is on surface. When the footing is on surface, then depth is going to be 0. Depth effect is also going to be gone. So cohesionless soil and footing on the surface, depth is also going to be gone. So now, what is the ratio between the ultimate bearing capacity, sir? So the ultimate by square 1.3 CNC plus gamma D NQ plus 0.4 gamma B and gamma. 0.4 gamma B and gamma. Just simply see, while I am reading the question itself, I am going to say, are a cohesionless soil, cohesion effect is going to be gone and rested on the surface, then depth is also going to be gone. Then what is remaining over here? Then what is remaining over here? 0.3 width effect and width effect. I hope you understood. And one more thing, the dia of the circular footing is the same as the side of the square footing. So which means the width of the square is nothing but dia of the circle. So both are same. When both are same, gamma B and gamma B and gamma is going to be same. Then the value is going to be 3/4, which is nothing but 0.75. So answer is going to be D. Answer is going to be D. See, just now I explained the topics and from those, mind it, I am not asking you to remember the formulae. I am asking you as a effects. When C0, cohesion effect is gone. When D0, D means depth of the soil is going to be 0, depth of foundation. Then there is no surcharge. Then what is the only effect? The only effect is going to be width effect. And in the case of circle, the dia and in square width both are same. So whatever the coefficients, 0.3 by 0.4, I can write directly 3/4 as 0.75. Okay. Yeah, some of the people, sir, they're asking 0.2 Q, right? Sir, in some textbooks, 0.1 Q, in some textbooks, 0.2 Q. Generally, 0.12 point Q isobar. Inside is pressure bulb. Inside is pressure bulb. So don't worry about that 0.1 Q or 0.2 Q. Generally, see, in some standard textbooks, they take as a 0.1 Q. In some other textbooks, they took as a 0.2 Q. So don't worry about that. Yes. You see, this is again one of the previous ESE question, 2015 question. In cohesive soils, the ultimate bearing capacity is independent. Okay. In cohesive soils, the ultimate bearing capacity is independent on the width of the foundation. Yes. So in the case of the cohesive soils, you know, CNC plus gamma D only, because I'll write gamma D and Q plus 0.5 gamma B and gamma. So in the case of the cohesive soils, as N gamma is equals to 0 and NQ is equals to 1, QU is equals to CNC plus gamma D. So number one, there is no width effect, and the ultimate bearing capacity of cohesive soil increases with the depth below the ground level. So as D increases, then Q is also going to be increases. Okay. So now this is also going to be true, but those are not going to be correct explanation. So statement 1 and 2 are correct, but not related. So these are some of the questions that I want to show you. Apart from that, there are some questions are there. We'll see slowly with respect to time. After the break, I'm going to solve more questions. We'll say all these things after the break. Okay. So So now have a break. It's 11:15. Have a break up to 11:35. 20 minutes break. So after the 11:35, we'll start the remaining topics. Means I have stopped here. That is that. Yes. So still some effects to be considered. We did not discuss about the water table yet. So when there is a water table, we have to look over the water table also. We'll see. We'll see those things after the break. So have a break, and we'll see after the break. Break is up to 11:35. Okay. Okay. Now, okay, now let's come to the next situations. So we have been explained about the ultimate bearing capacity for various type of footings and for clays. Now let's see for local shear failure. LSF. Look, in the case of the Terzaghi's theory, he assumed soil fails by general shear failure. But you know that the general shear failure and local shear failure can be seen in the case of the shallow foundations. So in shallow foundations, there is a possibility of local shear failure also when phi less than or equals to 28 degrees. So now, if that is the condition, then what is the corrections that we are going to do? Whatever the given equation, in the case of the strip footing, whatever the given equation is CNC plus gamma DNQ plus 0.5 gamma B and gamma. That's it. I go with the same conditions. I don't change any equation also. But now, in the case of the local shear failure, let's go back to the local shear failure. In the case of the local shear failure, the shearing is going to occur partial. Yes, partial shear happens means the total resistance is not going to be developed. So whatever the developed shear strength only we have to take. And in the previous chapter, we discussed that developed as a mobilized values. So in the case of the local shear failure, then now this C is going to becomes as a CM. C becomes as CM and NC becomes NC dash, NQ dash, N gamma dash. So my dear students, the equation is going to be same, but if I say the if I say the failure as a local shear failure, then here C becomes a CM and NC, NQ, N gamma becomes NC dash, NQ dash, N gamma dash, where NC dash, NQ dash, N gamma dash depends on phi m, where CM is mobilized cohesion, phi m is mobilized friction angle. Sir, how to find out the CM and phi m, sir? So this CM and phi m is given as CM is equals to 2/3 of C, whereas tan phi m is equals to 2/3 of tan phi. So how to determine the CM and tan phi m? Means phi m is CM is equals to 2/3 of C, whereas tan phi m is equal to 2/3 of tan phi. So if there is a local shear failure, you see in the examination, if they give you phi as a 20 degrees, there was one previous gate question, they have mentioned the phi value is going to be 20 degrees. As it is less than 28 degrees, then you are going to take it as a local shear failure. And see, this is no more NC, NQ, N gamma. These are NC dash, NQ dash, N gamma dash, depends upon phi m. And how to find out phi m, sir? Tan phi m is equals to 2/3 of tan phi. We'll see one previous gate question later. Now, let's see for water table. Now, the last one in this is effect of water table. effect of water table. Effect of water table. So now coming to the effect of water table, in this case, let's draw the figure once again. Okay. Yes. Look, this is the depth of the foundation, and if B is the width of the footing, then below the footing, the effect is up to this B only. Now let's see what is the effect of the water table. So now here, see if the shape is going to be changes, then you see 1.3 and 0.3 for circle, 1.3 for square, 0.4 for square, right? See, I just take for a strip footing. See, I just keep one thing in my mind, that formula is going to be based upon the Terzaghi for strip footing only, and I'll modify everything for that. If I give you shape, you have to introduce that. If I give you clay, you have to introduce. If I give you local shear failure, you have to introduce those. So now, if there is a water table, let's see if there is a water table. Here, let's take A. What is this A? Please come on, tell me. What is this A? Water table is located well below the base of footing. Water table is located well below the base of footing, or at a depth below the base of footing B. So A, when water table is located well below the base of footing, so come on, you tell me. Look, our effect is, you see the surcharge will be acting here, and you know our effect is going to be up to D plus B only. Yes or no? Our effect is going to be up to D plus B only. But the water table is going to be well below the base of footing. See, this soil is under submergence, but our discussion is all about in this zone and in this zone. Yes. So due to this water table, the effect on soil mass, the effect of water table on the soil mass above is not going to be, which means I can write no effect of water table. So when water table is located well below the base of footing, there is no effect. Then what is QU? CNC plus gamma DNQ plus 0.5 gamma B and gamma. But students, I am telling you once again, listen to this clearly. I am using this as a basic equation. And in the question, if they give square, you know what to do. 1.3, 0.4. And if I give you as a circle, you know what to do. 1.3, 0.4. Sorry, 0.3. And if I give you rectangle also, you know. So I take this equation as a basic equation and I'll modify everything through this equation only. So now let's go for B. If water table is going to be located at the base of footing. If water table is going to be located exactly at the base of footing. If water table is located at base of footing. So now you tell me, my dear student, if water table is going to be located at the base of footing, does this water table cause any effect to the surcharge? You know the surcharge is nothing but Q is equals to gamma into D. So if water table is here, whatever the soil in shear is going to be affected, not the soil above the base of footing. Yes or no? So now you tell me, if I say the water table is going to be at the base, it's at the base of footing, then what is the ultimate bearing capacity? CNC plus, is there any effect on the surcharge? No, gamma DNQ plus 0.5. Now you see gamma dash BN gamma. Why I took gamma dash BN gamma, sir? Because if the water table is going to be here, then whatever the soil below the water table is going to be completely submerged. So then gamma becomes gamma dash. I hope you understood. The point here is wherever there is a water table, below the water table, soil is completely submerged. Then you know that effective stress comes into existence. What is effective stress over here? In this zone, gamma dash into B. Now, similarly, let's see at C. If water table is located at ground level. So now, my dear student, an entire soil mass, see now, if the water table is going to be located at the ground level, entire soil mass is under submergence. Yes or no? When the entire soil mass is under submergence, then surcharge is going to be gamma dash, and in the shear effect is also going to be gamma dash. QU is equals to CNC plus now gamma dash into DNQ plus 0.5 into gamma dash into BN gamma. So observe these 3 points clearly. What I want to say here is, Hare Baba, below the water table, you take it effective stress. That's it. You take the effective stress, nothing mentioned. You take the effective stress. So no other option over here. You just take the effective stress. Now, initially, water table at A. So this is a soil, but our focus is on only this portion D plus B. So no effect on the water table. And now B, this is the water table, and this soil is going to be submerged. This is submerged. So here gamma dash into B and above gamma into D only. But if I say the water table is at the ground level, then the entire soil is under submergence. So I am going to take gamma as gamma dash. Mr. KP, sir, I can't see the screen like the lecture started. Is it the same for everyone? Okay, fine. I mean, if you have any problem, you please update the Zoom app. So if you can update the Zoom app, then there is no problem. Yeah, there is no problem for everyone. So my dear KP, so you please update the Zoom app if you have not done, and then check once again. Okay, fine. So now, I hope you understood what is the effect of these water tables. So then if you see, look, from these conditions, I can write a note point as in corrosionless soils, in cohesionless soils. What is the meaning of cohesionless soil? C is equals to 0. When water table rises from well below ground level to ground level, or yeah, I can write well below base of footing to ground level. Now you please tell me, everybody have a look. If I say cohesionless soil, then C is equals to 0, right? If I say C is equals to 0, now everybody, if I say C 0, gamma and gamma, yes or no? You take gamma as common out. You can take gamma as common out. If I take C0, then you can write QU as a gamma common. If you make sure this C is equals to 0, I'm not removing that. If I make sure C0, then I can take gamma common. And if water table is going to be rises up to ground level, if C is equals to 0, then I can take this gamma dash as a common. So now in the case of the cohesionless soil, when water table rises from well below the base of footing to the ground level, the unit weight has changed from gamma to gamma dash. Now you know that if I say gamma as 19, gamma dash 19 minus 10, 9. So almost 50% of the bearing capacity is going to be reduced or not. First of all, gamma is more or gamma dash is more? Gamma is more. Gamma is going to be more. So if water table rises from well below the base of footing, you see here, from here to here, then the unit weight of the soil is less. Then the effective stress is going to be decreases. I hope you remember chapter number 7. When water table rises, effective stress decreases. And when the effective stress is going to be decreases, strength decrease, bearing capacity is also going to be decreases. Now I can see over here, gamma change it to gamma dash, gamma change it to gamma dash. So ultimate bearing capacity reduces by almost 50%. See, I am writing a point almost. I am not saying exactly 50%. I am writing almost 50%. So I hope you understood. The point over here is that there is no need of remembering all these things here. You want to remember all these things. Wherever there is a water table, below that, just keep gamma as gamma dash. That's it. Now, let's see what happens. If there is a water table here, let's see what happens if there is a water table here. Similarly, let's see what is the effect of water table at this condition. So now, my dear students, at first I have explained you A, B, C. Now, if there is a water table located, at a depth of ZW1 below the ground level. So let's take it as E. And mind it, this ZW1 is a range of 0 less than or equals to ZW1 less than or equals to D. The meaning of ZW1 is what is the depth of water table below the ground level? What is the depth of the water table below the ground level at a depth of ZW1? See, if the water table is at ground level, then what is ZW1? 0. If the water table is at ground level, then what is ZW1? 0. See, I am giving you the range of ZW1. And if the water table is going to be at the base of the footing, what is ZW1? D. So the ZW1 ranges from 0 to D. So this ZW1 is going to be seen in the case of the depth, means a surcharge effect only. Okay. Now, come on, my dear. If this is ZW1, then what about this depth? D minus ZW1 or not? Everybody? Okay, this is D, right? D. If water table is at a depth of ZW1 below ground level, then what is ultimate bearing capacity? Simply effective stress CNC plus, now you know above this water table gamma, below water table gamma sat, and as it is effective stress gamma dash R naught. So now in the case of surcharge, what is the surcharge acting over here, please? What is the surcharge acting over here, please tell me? Gamma into ZW1 plus effective stress, right? When there is a water table, you have to take the effective stress. Gamma ZW1 plus gamma dash into, see this total depth is D and this is ZW1. So D minus ZW1 into NQ into NQ plus now you see whatever the soil below the base of footing, let's remove this one first of all. Whatever the soil mass below this footing, this is going to be completely submerged or not. See, if the water table is here, above footing partially submerged, below footing completely submerged. Completely submerged means gamma dash 0.5 gamma dash Bn gamma. I hope you understood. So if water table is at ZW1 below ground level, then in that zone, there is going to be above water table gamma, below water table gamma dash. Now let's see the last condition, E. Now, if the water table is located at a depth of ZW2 below the base of footing, ZW2 below the base of footing, again 0 less than or equals to ZW2 less than or equals to B. I am taking some depths rate, that's it. What about pore water pressure? आप कहाँ है भाई? Effective stress, if I take effective stress, then where the effective stress is nothing but total stress minus pore water pressure, right? What is effective stress? Total stress minus pore water pressure, right? So it has been already included. So now, if the water table is here, let's see. If the water table is here, the water table is below the base of footing or not, so no effect on the surcharge. No effect on the surcharge. So if water table is at a depth of ZW2 below footing, then QU is equals to CNC plus gamma D and Q. There is no change at all. Gamma D and Q, because the water table is where? Here at E. So above there is no weight, plus 0.5 into gamma ZW2 plus gamma dash into B minus ZW2 into N gamma, because this is gamma and this is gamma dash, gamma into ZW2, and this value is going to be B minus ZW2. So these are the conditions over here. So please have a look once again. This is B. If you ask me, sir, did I have to remember all these things? No, you don't need to remember. What you know is, wherever you see below the water table gamma, gamma dash, above gamma, that's it. Which means simply you find out effective stress, that's it. So have a look over here, please. First you see these figures and then you can look over this one also. Yes, these conditions are important for ESC also. So how to find out ZW1 and ZW2? They'll give you, Baba, they'll give you. For example, if I say the depth of foundation is example, the depth of foundation is 2 meters. Water table is at 1 meter below ground level. Then what is ZW1? 1 meter, right? How to find out ZW1? So C dash, forget about C dash or phi dash. I'm just representing C phi. Now I don't discuss about C dash, phi dash or CU phi U. That values are going to be undrained or drained, that you have to do in the laboratory, not in the field now. So yes, done. Is depth of foundation D. Yeah, if water table is at D, yes, there is a, see, if there is a water table, below the water table soil is completely submerged. Okay, I write that. Below water table soil is completely submerged. Unsaturated also, but we don't, we want effective stress only. So see, below this, we have to take this effect. Whatever the base width, below the base of footing, that much width only we have to consider. That's what Terzaghi said. Go back to Terzaghi. That's what Terzaghi said, B only. So now if you have completed now, let's see, there is a one more formula, approximation method. And this approximation method says that QU is equals to CNC plus gamma D into NQ plus 0.5 gamma B into N gamma. This is the same equation. Please go through this if you want. You want to go for that. You want to go for that, and if you want to see, you see. If you don't understand these things, you don't understand the effective stress concepts. That's it. That's for sure. And if you are spending too much of time in this topic, then you don't understand the effective stress at all. Sir, if there is a capillary pressure, if they give, they can, you can consider, right? If they give, you know how to find out that. Sir, are we going to study Meyerhof theory? Yes, my dear friend. We are not going to die tomorrow or today, so don't worry about that. This chapter is full of formula and less conceptual framework. I think you have attended the class just now. If you have attended the class the earlier and before, means yesterday also, you would have filled this chapter. I have been explained with the figures and all those things also. Okay, fine. So now there is a one more approximation method. Sir, instead of going all these things, the approximation method, say approximation method is meaning is an approximation. You cannot use each and everywhere. If they ask you, else multiply with RW1, multiply with RW2, where RW1 and RW2 are water table correction factors. Water table correction factors. Sir, what is this water table correction factors, sir? You see, whenever there is a water table, what is going to be happen? The gamma is going to be changes to gamma dash or not? Yes or no? So you can directly find out by means of the water table correction factors as RW1 is equals to 0.5 into 1 plus ZW1 by D. RW2 is equals to 0.5 into 1 plus ZW2 by B. Sir, what is this RW1, RW2? That's the reason why I have given the ZW1 and ZW2. I'll explain. Wait. Look. Go back over here. Now, if you observe, what is ZW1? Depth of water table below the ground level and above the footing. And what is ZW2? Depth of water table below the base of footing and above the depth. So this is ZW2 is a depth of water table below the base of footing and less than B, where ZW1 is depth of water table below ground level and above base of footing, whereas ZW2 is depth of water table below footing base. As you know, ZW1 0 less than or equals to ZW1 less than or equals to D, which means depth of water table at the ground level ZW1 0, at the base of footing D, and in between ZW1 0 less than or equals to ZW2 less than or equals to B, which means depth of water table, if the water table is going to be at the ground level. Now you see, observe, I am going to end these conditions now. Observe here, this RW1 is equals to, what is the RW1 factor? This is going to be done in which frame? This ZW1 is going to be lies below the ground level and above the footing, which means the effect of surcharge are not. So then I multiplied with a gamma D into NQ RW1. This is a surcharge effect. This is a surcharge. And if there is a water table in the surcharge, this is a surcharge, right? If there is a water table in the surcharge, so the water table correction factor is RW1. And now come to here, this is nothing but a width effect, right? This is nothing but the width effect. So as it is a width effect, now below the water table, below the footing, if there is a water table, the effect of water table is represented with RW2. Now, if water table is well below base of footing. Now come to this point. If the water table is going to be well below base of footing, what is ZW2, please? Come on, tell me, Nana. What is ZW2? Here, what is ZW2? ZW2 is B. And what is ZW1? Obviously, ZW1 is from ground level to the base. As the water table is below the base, then ZW1 is going to be D. So if water table is well below the base of footing, then ZW1 is equals to D. ZW2 is equals to B. Okay. So now what is RW1? 0.5 into 1 plus d by d, which is going to be 1. RW2 0.5 into 1 plus d by b, which is going to be 1. So now what is RW1 and RW2? 1 and 1. Then you can write QU is equals to CNC plus gamma DNQ RW1 plus 0.5 gamma B and gamma. I hope you understood now. Does this formula, see, this is the condition if water table is well below the base of footing or not. And does this formula and this value is going to be same or not? Yes. See, that's just based upon the location of the water table, you have to check. ZW1 is below the ground level and above the base of footing. If the water table is below the base of footing, then ZW1 is going to be D. The maximum value of ZW1 is D. The maximum value of ZW2 is B. Now, let's say if water table is located at the ground level, if the water table is going to be located at the ground level, see, if the water table is going to be located at the ground level, you see, then what is ZW1? 0. What is ZW2? 0. ZW1 is going to be 0. Then what is RW1? 0.5 into 1 plus 0 by D, which is going to be 0.5. ZW2 is equals to 0. Then what is RW2? 0.5 into 1 plus 0 by B. This is going to be 0.5. Okay, so my dear, day by day you are neglecting doubts, questions, queries and all, fully ignoring all the things. You're not giving assignments. You said there will be doubt clearing session on 8 p.m. but there is nothing. As the days are passing, you are not taking any care of the students. This might sound harsh, but this is what I and many of the students are feeling. Sorry. Okay. As you have asked me, now I'll let you my schedule. Okay, fine. If you feel so, I am so free, then you tell me. Every day from morning 9 o'clock to 1:30, I have online session. And afternoon 2:30 to 7:30, I have recording session. And after coming from the 7:30, by 8 or 8:30, I have to prepare the questions for your test series. And then whatever the recorded videos I have to do, I have to review that. And every day by the time I sleep, you don't believe me, I sleep not less than 2 a.m. I mean, every day it reaches 2 a.m. or 3 a.m. also. Today morning also I slept at 2:45. And meanwhile, I am providing the questions for you. And you see, I mean, the person who has sent this message. So if you have any friends in other departments, means mechanical department or apart from the civil, there are some other classes are going on, you please ask them. You just open whatever the login details, I have provided a folders for you. I am providing you my notes and I am doing the PDF and I am sending on my own. Do you think it is going to be easy? And it takes minimum 20 minutes. And no other faculty is going to do that. And I'm providing you the short notes and I'm providing you more number of the gate questions. So I have provided all the resources and I am doing all the things that I can do. And meanwhile, from day starting to day ending, I get messages through Telegram, I get messages through mail, and some of the people may get messages through my WhatsApp also. So whenever there is a possibility, I may not give the reply within a minute, but I definitely give the reply to them, even if it's a small question or large question. And if you have any doubt, as you said, some of my students are feeling, yes, you can ask those students what they're feeling also. So I don't have a minute, even during this lockdown period also, I have busy works and I was never a free person. whatever the free time I have to there, I have to spend with my family also. And my personal time at this point of time is 0. So if you feel so, I'm sorry for your feeling, but I cannot do anything. And I reduce the assignments just because I want to consider all those things in the test series. I want to consider all those things in the test series, or I can give you as a whole bunch, so that while you prepare the questions. And one more thing you're asking us, you're neglecting doubts and questions. Yes, I neglect the doubts which are silly, definitely. And questions means once you complete the chapter, once I complete the chapter, then only you will get to know what is the actual reality in that chapter. For example, you go to movie, and by the time of interval, you will ask everybody, "Arey yaar, what is this movie? And does this movie end over here? When the movie is going to be end? And what we learn from this movie?" You have to wait to reach the end and the climax of the movie. Then only you can judge whether the movie is going to be good or bad. Yes or no? Just because you have seen 5 minutes of scene and you're going to come out and judge, just like to the viewers, this movie is faltu. Just like you watch a 5 minutes or 5 minutes of review. Is it? Okay, fine. I mean, it's not about irritating, or it's not about like, I mean, I'm not getting angry or I'm not getting irritated over here. I'm just saying, see, it's like a level of perception you are having. Just because you have one perception, that is not true, my dear. Everybody have perceptions, you and me have, and everything is a perception. There is no right, there is no wrong. Just because you are feeling you are right, that's not going to be right for everyone. So think of it. Okay, fine. Now RW1 and RW2. So this RW2 is going to be 0.5. And now I hope you understood what is the meaning of ZW1 and ZW2. So if water table is located at ground level, then the ZW1, depth of water table at ground level, ZW1 is going to be how much? 0. And ZW2 is also going to be 0. Then RW1 and RW2 is going to be 0.5. Then you see what is QU? CNC plus gamma DNQ into 0.5 plus 0.5 gamma B and gamma into 0.5. For cohesionless soil, C is equals to 0, then QU is equals to 0.5 into gamma DNQ plus 0.5 gamma B and gamma. Similarly here, for cohesionless soil, C0, right? Then what is QU? Gamma DNQ plus 0.5 gamma B and gamma. So my dear student, please observe, by this approximation method that I can say that if water table is well below the base of footing, this is QU. And if water table is located at ground level, this is QU. What is the difference from here to here? 0.5, which means when the water table is going to be rises from well below the base of footing to the ground level, in the case of cohesionless soil, the ultimate bearing capacity is going to be reduced by 0.5, which means 50%. So that's the reason why I said this condition. So I hope you understood. Here the values are going to be, these are the water table correction factors. These are nothing but water table correction factors. They can ask you in the case of ESC. In ESC, they can ask you this type of questions. So with this, I have completed the effect of water table also. So that's about Rankine's theory. Still, I did not discuss any other theories. I discussed about only Rankine's theory. Only give me a minute, please. So please have a look once. Once again, you please have a look about this. Then I'll be discussing about this Rankine series quickly. Okay, fine. So that's all about the. See, let's have a look once. In this total theory, I am using only one equation, and in that equation only I am going to do all the conditions. So my dear students, listen to me. I am going to take a quick review over here. So according to Terzaghi, the soil fails by general shear failure and base is going to be rough, and the side resistance is going to be neglected. So I have given you the equation as a three conditions. So that one is cohesion effect, surcharge effect, and width effect. So where NC, NQ, N gamma depends upon the 5 values, and if it is a clay soil mass, you have to remember the NC, NQ, N gamma. So in the case of clays, NC is going to be 5.7 when base is going to be rough, and 5.14 when base is going to be smooth. So NQ is equal to, sorry, NQ is equals to 1 and N gamma is going to be 0. So if you substitute all these things, I can say in clays, QU is independent on the width of the footing and whatever the net ultimate bearing capacity, cohesion effect CNC. And if there is any shape of the footing, see for the strip, and now from where you can see in the case of the various shapes of the footing, circle and square, cohesion increases by 30%, whereas the shape circle 0.3, square 0.4, strip 0.5, and in the case of the rectangle 0.5 into 1 minus 0.2 B by L. And then whenever there is a local shear failure, see this equation is for whom? General shear failure. But when there is a local shear failure, you know, in local shear failure, the shear is going to be mobilized partially. So instead of C, I am going to use CM. What is CM? 2/3 of actual C. Instead of phi, I am going to use phi M. What is phi? Phi M, tan phi M is equal to 2/3 of tan phi. See, if I change the phi to phi M, NC, NQ, N gamma depends upon phi. So when I change it to phi M, then it is going to be changes to NC dash, NQ dash, and N gamma dash. And coming to the effect of water table, wherever there is a water table, below that water table, simply effective stress. If the water table is here, nothing. But if the water table is at ground level, entire is going to be submerged. So you take it as gamma dash and gamma dash. So, and the water table correction factors, I simply say, take it as effective stress only. Water table correction factors, these are the water table correction factors. ZW1 is the ZW1 is from the ground level to the base of footing, and ZW2 is from the base of footing to the point where it is going to be nullified. So that's about these conditions. Now, the limitations of this Rankine's theory, sorry, Terzaghi's. Theory. Shallow foundations suitable for only shallow foundations. The first limitation is going to be suitable for only shallow foundations. Yes. So in the case of this suitable means now apart from that, the limitations of Terzaghi's theory, apart from that, so you can see so far and so good, whatever the load I have taken is known as a concentrated load. Yes or no? But in reality, there might be some eccentricity. We did not take care of that. And in reality, the load can be some inclined also. See, in the case of the mountains, the footings are going to be provided with some inclination also. The footings are going to be provided with some inclination also. So that inclination has been accounted. And as it is going to be shallow foundation, so for the deep foundation, it is not going to be accounted. It is not going to be accounted. Inclination has not been taken care. Shapes has not been included. Shapes, comma, inclination, and depth factors are not included. So what is the meaning of shapes? Rectangle, circle, square. See, instead of going for different formulas, I have to give for one factor. Just like NC, NQ, N gamma. What is mean by NC, NQ, N gamma? Bearing capacity factors, right? Just like that, in Terzaghi, he did not give you any other factor. So he has given only bearing capacity, but he did not mention any shape factor or any inclination or depth. So what is the representation of depth, sir? He did not consider for the deep foundations. He considered only for the shallow foundations. So these are the limitations of Terzaghi's theory. Now, let's come to the next theory. Skempton's theory. So that's about the Terzaghi's theory. Now come to the Skempton's theory, and this Skempton's theory is completely suitable for clayey soils in undrained condition. So suitable for clayey soils in undrained condition. So as it's a clay, you know that the net ultimate bearing capacity of clay. So what is the net ultimate bearing capacity of clay? Please tell me. What is the net ultimate bearing capacity of clay? CNC, yes. So the net ultimate bearing capacity of clay is going to be CNC. As simple as that, I am telling you again, what is net ultimate bearing capacity of clay? Cohesion effect. But mind it, this NC is not going to be same. This NC is 5.7 in the case of Terzaghi. This NC is 5.14 in the case of Prandtl. Now, according to Skempton, this NC is equals to 5 into 1 plus 0.2 into D by B in the case of strip footing. 5 into 1 plus 0.2 into D by B. This is very, very important. 5 into the factor is not going to be 5.7 now. 5 into 1 plus 0.2. What is mean by D? Depth of foundation. B is width of foundation. 5 into 1 plus 0.2 D by B into 1 plus 0.2 B by L. This is for the rectangular footing. This is for the rectangular footing. And if you know this rectangle, then you can write down if B by L is equals to 1. If B by L is equals to 1, then 1 plus 0.2, 1.2. 1.2 into 5, 6. So in the case, this is for the rectangular footings. So now that's it. So in the case of the Skempton's theory, the NC value is no more 5.7. Sir, see, all these theories are to determine the ultimate or net ultimate. Once you find out those, then you have to find out the values as this one. So whatever this is, once you find out those things, then you have to use the design condition only. That's about the Skempton's theory. This is suitable for suitable for shallow and deep foundation. Sir, why I am saying this shallow and deep foundation, my dear student? Now you tell me, I have taken depth into the consideration or not? As the depth changes, the NC is also going to be changes. But in the case of Terzaghi, no matter whatever the depth, NC is going to be 5.7, that you know that. But in the case of the Skempton's theory, as the depth changes, the NC is going to be changes. So it has taken the depth consideration. So this is going to be suitable for the shallow and deep foundations. See, these are all just modification theories, that's it. We don't need to go too much into this one. Next, last theory for today's, we'll solve some problems. Meyerhoff's theory. And this Meyerhoff theory is suitable for all soils and all foundations. It has included inclination and shape of footing also. It has included a inclination and shape of the footing also. These are just modifications. These are just modifications, sir. So in the case of this, see, some of the asking, sir, if it is going to be circular footing, sir, circular footing and square footing. See, circular footing and square footing. See, in the case of circle, width and length both are going to be same. Then there it is going to be the dia. B is going to be dia of the circle. Just same thing for the square and circle. So in the case of the Meyerhoff theory, as I said you, it is suitable for all type of soils. Now, whatever you know, you just write. You know that QU is equals to CNC plus gamma DNQ plus 0.5 gamma B and gamma. So I don't want to go for any other equations. I will use the basic equation. And in this equation only, I am going to take the modifications. So what is the limitation of Terzaghi? He did not consider shape, but Meyerhoff considered. He did not consider inclination, but Meyerhoff considered. And he did not consider depth, but Meyerhoff considered. Now, this is the equation from the Terzaghi, right? Now, as he considered all the other effects, now simply, my dear students, if it is going to be depth, DC, DQ, D gamma. What is this DC, DQ, D gamma, sir? Depth factors. SC, SQ, S gamma. IC, IQ, I gamma. The equation is going to be same. The equation is going to be same, but apart from this NC, NQ, N gamma, I am representing all the other factors. So this equation is going to be suitable for any type of soil, any type of foundation, any shape of footing, and any type of inclination also, where DC, DQ, D gamma are depth factors, SC, SQ, S gamma are shape factors, IC, IQ, I gamma are inclination factors. Inclination factors. So this is nothing but the Meyerhoff theory. DC, DQ, D gamma, depth factors, and SC, SQ gamma, shape factors. So these are the factors. That's it. See, these are factors has not included in the Terzaghi, and they were included in the Meyerhoff. And now, sir, if there is a water table, you know it. See, now if I give you these factors, You don't need to apply 1.3 CNC, something like that, because they have considered all those things, right? But if there is a water table, you know it clearly. If there is a water table, gamma becomes gamma dash. I hope you understood this. Now let's solve some questions. So in examination, do they give factors? Yes, they'll give you. Okay, fine. Yes. So now if you have completed, let's solve some questions. Yes, these methods are important. These are just changes in the previous methods. These are important only. I'll show you. I'll show you. Wait. Okay. Now everybody have a look, please. Stop your writings and listen. These are classroom practice questions. When I show you the number, these are classroom practice questions. These are classroom practice questions. You see, I have sent you the PDFs, right, for you. You can look over there also. So these are classroom practice questions. Now, a footing 3 meters square. Keep that in your mind. What is that? 3 meters square. So square footing. So 3 by 3. Is carrying a gross pressure. What is meant by gross pressure? Q. 350 kilonewton per meter square at a depth of 1.2 meters. The saturated unit weight of the sand, gamma sand, is 20 kilonewton per meter cube, and unit weight of soil above water table is 17 kilonewton per meter cube. The shear strength parameters, C dash is going to be 0 and phi dash is going to be 30 degrees. For that, NQ is going to be 22 and then gamma is going to be 20. Okay. Now what they're asking is determine the factor of safety with respect to shear failure. I told you most of the failures are shear failures. Go back. Look over this condition. What is this? Most of the soils fails by shear failure. As most of the soils fails by shear failure, then the design condition is going to be Q less than or equals to QS. Q less than or equals to QS. Now, my dear, they're asking about whom? They're asking about the factor of safety. Keep that in your mind. When they ask the factor of safety, so look, width, depth, load, factor of safety. These are the 4 design conditions. Width, they'll ask you to find out width. They'll ask you to find out depth. They will ask you to find out the factor of safety. They'll ask you to find out the load also. So now what they're asking is a factor of safety. Yes? Okay. Let's see. Let's draw the figure also. Okay, fine. So from the figure, I can say whatever this depth, this is known as the depth of foundation, which is going to be 1.2 meter. And what is width? 3 meters. You know that the footing is going to be have an effect of depth, which is going to be exactly 3 meters only. So whatever the below the footing up to this point, there is an effect. Yes or no? Now, so if this is the condition, what is the total gross pressure acting? What is the total gross pressure acting? The total gross pressure is given as Q. So now, my dear student, what happens for the factor of safety? Water table is 5 meters below the ground level. अरे बाबा ये total क्या है? ये total itself is 4.2 meters. If the water table is going to be located over here, so this is 5 meters. As water table is going to be located well below the base of footing, and B is going to be exactly at the base of footing. B, because it is going to be 1.2 meter. See, I have given you these conditions. Now I am asking you to find out the factor of safety. I am asking you to find out the factor of safety. Okay, listen. First of all, given footing is square. When the given footing is going to be square, what is the ultimate bearing capacity? 1.3 CNC plus gamma D NQ plus 0.5 gamma D N gamma. Ye water table is at 5 below footing. Water table is at 5 meters below footing, which means no effect of water table. No effect of water table. What is 0.4? Okay, fine. Oh, okay, sorry. 0.4. Yes. 0.4 gamma B and gamma. See, water table is 5 meters below the footing, no effect of water table. So I don't go with B. I don't go with A. I'll go with B. I'll leave you the A as an assignment for you. I'll give you A as an assignment for you. I'll go with the B because water table is at 1.2 meters below the ground level. Yes. So given water table is at 1.2 meters below ground level, which means at base of footing. So now you apply the conditions. If you apply the condition, what is QU then? CNC 1.3 CNC plus gamma DNQ. Now you tell me, look, if the water table is here, then whatever the soil below is going to be submerged or not? Plus 0.4 gamma dash BN gamma. See, I will writing every point here, but from the next question onwards, I don't write all these points. Keep that in your mind. Now, given C is equals to 0, yes or no? So C is equals to 0 given, and C dash is equals to 0. So now let's take C dash and phi dash because the NC, NQ, and gamma also depends upon the C dash and phi dash. So now this is going to be QU. Fine. Don't apply anything. Don't apply anything. Just you keep this aside. Now, what is QNU? QU minus gamma D. Gamma D NQ plus 0.4 gamma dash BN gamma minus gamma. First, you habituate with the procedure. Now, can I take gamma D common? Then gamma D common means NQ minus 1 plus 0.4 gamma dash BN gamma. So this is net ultimate bearing capacity. See, what I have done is at first, as it is a square, I have written the equation and water table is there. I applied the water table and there is C dash. So I removed the C and then I find out the net ultimate bearing capacity. So now I am asking you factor of safety. Now, what is the design condition? The design condition here is Q should be less than or equals to QS. Q should be less than or equals to QS. What is Q? Gross pressure. This is gross pressure. And this is SBC of soil, which means safe bearing capacity of soil. And I can write this one as Q is equals to QS. Means at a critical condition, Q is equals to QS. And now, what is QS? How to find out QS, please? QS is equals to, how to find out QS? QS is equals to QNS plus gamma D. Okay? QNS plus gamma D. What is QNS? QNU by factor of safety plus gamma D. Then this is the condition, right? So now I can write directly this one over here as QS is equals to QNU by factor of safety. Net ultimate by factor of safety is going to be whom? Net safe plus gamma D. So now, my dear students, you apply QNU over here. The given Q is going to be how much? 350 kilopascals. So apply 350 is equals to QNU, gamma DNQ. First write down the equation. So Q is equals to gamma D into NQ minus 1 plus 0.4 gamma dash BN gamma by factor of safety plus gamma D. I hope you understood how I have written this equation. Yes or no? I hope you understood how I have written this equation. So from this condition, I can write Q is equals to QS, and that QS is nothing but, what is QS? Safe. Safe means net safe plus gamma D. And what is net safe? Net ultimate by factor of safety plus gamma D. Okay. Now, if you observe, look, substitute the values. I want the factor of safety.